In this lecture, we're going to talk about the binomial theorem. This is going to be the last section of chapter 14 for us. Here I have a list of exercises from the book, your book. Again, the highlighted items are the ones that are part of your homework, and the ones that are highlighted with a green dot next to them are the ones that we're going to look at together. And with that, let's begin this section. Now, before we actually take a look at the binomial theorem, I would like to do the following. Let's talk about factorials. Okay, and then we actually talk about the binomial theorem once we do that. So let's begin by talking about factorials. Now, for every whole number, remember whole numbers are 0, 1, 2, 3, 4, and so on. There is one characteristic of whole numbers, one thing we can do to them, and that is the factorials. We can actually evaluate factorials for these whole numbers. So, for example, what do we mean by that? Here's 3, and the factorial symbol is that exclamation mark. So the exclamation symbol means factorial. Okay, so what does that mean, 3 factorial? Well, this means product of 3 and every whole number up to 1, actually down to 1. So that means 3 by 2 by 1, and that would be 6. So there is 3 factorial. What is 4 factorial? That means 4, 3, 2, 1. And that product's going to be 24. And so on and so forth. So, for example, 7 factorial, that's going to be 7, 6, 5, 4, 3, 2, 1. So it's always the product of that number and every whole number down to 1. And the 7 factorial here is going to be 7. And I actually have a calculator that's capable of doing factorials. I'll show you in a moment how to do this. There you go, 5040. Notice the growth from 4 to 7 factorial. We went from 24 to over 5000. So these factorials are actually functions, and they're quite elaborate, but we're just going to briefly mention them because we're going to use them in the binomial theorem in this section. Now, with factorials, 0 factorial is equal to 1 by definition. Okay, and we'll again look at these on the calculators in just a moment. Now, in general, the n factorial, where n is like a natural number, is given by n, product of n by n minus 1, n minus 2. See, the numbers are getting smaller. Dot, dot, dot. 3 times 2 times 1. So again, it's product of n and every natural number down to 1. Okay, so that's what that is. So let's take a look at, to begin with, some exercises here. First, we're going to look at exercise number 12. In exercise number 12, quite easy, we're given 9 factorial. So that means 9, 8, 7, 6, 5, 4, 3, 2, 1. Now you can actually multiply these one at a time, or if you have any kind of calculator, most calculators, now scientific calculators, have a factorial button. So my calculator shows this number to be 362,880. And again, I'll show you in a moment how to do this on a TI calculator. Let's take a look at exercise number 16. In number 16, this time I want to do 12 factorial divided by 10 factorial. Okay, so what does this mean? Again, this means 12, 11, 10, 9, 8, dot, 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 all the way down to 1, right? Divided by 10 factorial is 10, 9, 8, dot, 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 all the way down to 1. Now, one thing I could do, I could actually use a calculator to do 10 factorial or 12 factorial divided by 10 factorials, or the way that I have written this out, you can see that this product, 10 all the way down to 1, is the same as this one. So I can actually use my calculator and multiply those two numbers, simply 12 times 11, and that's going to be the product, 132. Okay, so this is how the factorials work. Let's try another one. This next one is number 18. And for this one, the problem has us do 10 factorial divided by 6 factorial, 4 factorial. Now the way the denominator is written, this is implied multiplication of 6 factorial times 4 factorials. So again, if I write this out, what does this mean? This means 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. If you really write every single factor out, the bottom is 6 factorial, 6, 5, 4, 3, 2, 1. 4 factorial, 4, 3, 2, 1. And again, I can cross out 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, top and the bottom. And then what remains? The remaining numbers or factors. In the denominator, I have 2 and 4 makes 8, and the 8 on top, those cross out. And I also have this 3 on the bottom and 9 on top. The 3's cross out. Notice everything in the denominator has divided out. And in the numerator, I simply have a 10, a 3, and a 7, right? And that product's going to be what? 210. So this is how we can actually evaluate these factorials. Now let me actually go to my TI calculator, and I'll show you how to do this in the TI calculator. Okay. So now I actually have what we call a TI emulator. That means it imitates. There you go. This is for like a desktop. So this is what the TI-84 Plus looks like. So let's begin with 9 factorial. Okay, exercise number 12 was 9 factorial. So if you have this calculator, this is how you would do it. You click 9. Now everything is showing up in here, right, in this window where you have larger screen, or you can look at the screen on the calculator. Now to get the factorial button, you click on the math button, and then you right arrow 1, 2, 3. Notice in here it goes to PROB, prob, that means probability. Then we're going to arrow down 1, 2, 3 from where it was, and there's a factorial symbol, and hit enter, and that's 9 factorial. Enter again, and you get the number that we had, 362,880. Let's do number 16. In number 16 we did 12 factorial, so there's going to be 12 math, go to prob, down to factorial, enter, that's 12 factorial, and then divided by. So I'm going to go divided by 10 factorial, so hit 10, and then math button, go to probability, down arrow to factorial, enter, and enter again. And there you go, 132. That's what we had before also. Now let's take a look at the one we did, number 18. And just to show you what that one was, in number 18, that was 10 factorial over 6 factorial, 4 factorial. So for this one, it's going to be, I'm going to go 10 math, enter, 10 factorial. Now we want to divide this, right? So I'm going to go divided by. Now in the denominator, because we have 2 items, 2 numbers we want to factorial, so I'm going to use parentheses. Otherwise the order of operation will be incorrect. It will be done incorrectly. So I'm going to go 6 math, go to prob, 1, 2, 3 down, 6 factorial, hit enter. Okay, and then we're going to multiply this by, go times 4 factorial, 4 math, and then again go to prob, 1, 2, 3, 2 factorial, enter, and then close parentheses. There you go. Now the order of operation, remember, parentheses gets done first, then 10 factorial gets divided by that. Okay, and hit enter again. We get 210, and that's the number that we had before. Now something here to show you, If I do 10 factorial divided by, if I switch 6 factorial, 4 factorial here, right? Instead of 6 factorial times 4 factorial, if I go 4 factorial, 6 factorial, it will be the same answer, wouldn't it? This is what I mean. If I go 10, and the reason I'm mentioning it is because we're going to see expressions like this in a few minutes. Prop factorial, enter. So I'm doing 10 factorial divided by parentheses. Instead of 6 factorial, 4 factorial, I'm going to do 4 actually factorial, enter, and then multiply that by 6 factorial, 6 math prop, you go down to factorial and enter, close parentheses, enter. So you see that it doesn't matter because again multiplication is commutative, that's the reason. Okay, so there we have it. Now let's take a look at this notation. So we're done with TI for now until we come back to it in a few more minutes. So let me minimize this, and what I want to do is I want to bring this up. So we're going to look at this notation, okay, which is in your book. Remember, a notation means a way of doing something. So this notation we have, which is parentheses n r close paren. Now the one thing that this is not, let me write that, this is not n divided by r. Okay, that's not what this is. It's not division. It's NR notation. So what does NR notation mean? Well, if n and r are non-negative means they have to be positive, right? Integers, and n is bigger than, greater than, equal to r, means the top number is larger than the bottom number, or at most they're equal. Okay. And how do we read this NR notation? It's read as n choose r notation. Okay, that's what it's read as, n choose r. So what does that mean? Notice in here it says it means, so it's a way of doing something. So what this means is actually what's to the right of it. It means this fraction. Okay, so in other words, I can write the NR notation as NR is equal to n factorial n minus r factorial times r factorial. That looks like example exercise number 18, doesn't it? The one we just did, the very last one. See, it has that structure. Now, this is actually this notation. It's also written in this form. You see this? NCR notation. So the C in the NCR or CNR notation, the C here stands for combination. Okay, that's what that is, a combination. Now, this is actually used in an area of mathematics called combinatorics, where we actually count things using permutations, combinations, things like that. So that's what that combination is. And I'll explain later on what the CNR does for us through an example. The very last exercise we do in this section, in this video, I'll try to clarify what exactly this notation is calculating or computing for us. Okay, so let's actually do an example of this. So in this example, what we want to do is the following. We're going to do exercise number 20. Okay, in exercise number 20, we actually have the 8-5 notation. So how do we read this? We read this as 8 choose 5, just like it's up here. 8 choose 5. That's how we're going to read that as. Now, going by what it means fraction, 8 factorial on top, that's n, right here. Let me write n is 8, r is 5. The lower numbers r, the higher number is n. I mean, you never switch those. We don't write 5 on top, 8 on the bottom. The top number must be greater than or equal to the bottom number. Now, in the denominator, we have parentheses n minus r, factorial that, and then r is 5 factorial. Now, the way to do this, in the numerator, I had 8, 7, 6, 5, 4, 3, 2, 1. In the denominator, 8 minus 5 is 3, right? But it's factorial, so it's 3, 2, 1. 5 factorial is 5, 4, 3, 2, 1. And there you go. If you do this correctly, everything on top will be in the form of multiplication, and so is everything in the bottom. Now, if you look at this again, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, those cross out. 3 times 2, 6, and the 6 on top crosses out, so the answer to this is going to be 56. Okay, that was pretty simple, right? Not bad. So that's how you can do this. Let's take a look at number 26. And then we go to our TI calculator. Number 26, I have 35, 2. 35 choose 2. So what does that mean again? That means 35 factorial, 2 factorial. Actually, let me write it exactly like it is up here. What am I looking at? I'm looking at this right up here. So it's in parentheses n minus r, right? So that means 35 minus 2 factorial, and r is 2. That's 2 factorial. So the denominator is going to be 35 minus 2 is 33 factorial, and 2 factorial is 2 times 1. Now in the numerator, I have 35 factorial. It means 35, 34, 33, 32, 31, 30, all the way down to 1, right? But notice how I stopped at 33 and used the factorial symbol here. That means there's no need for me to write it all the way down to 1. That's what that 33 factorial is. And the reason I stopped there is because if you look at this 33 factorial here and 33 factorial here, see, they're the same numbers, right? Whatever they are, there's going to be a huge number, but they're going to cross out. So now I can actually work this thing. 2 and 34, that's 17, right? 17 times 2 is 34. And I can do 17 times 5. I'm sorry, 17 times 35. That's going to give me 595. Okay. And there you go. That's the combination 35 choose 2. 595. Now, let's actually do these in StatCrunch. So I'm just going to quickly make a note of these so I have it. So the bottom number is 595. The top number turned out to be 56, right? Okay, let's go to our TI calculators and let's actually do this. So I'm going to TI calculator. So here's how we're going to do this. Let me clear the slate. Okay, so let's do 8 choose 5. To do 8 choose 5, you're going to click or hit 8 on the calculator, then math. You go to prob for probability, and this probability, for those of you who take statistics, because there's a lot of probability that works into statistics, so you will actually use these ideas in your statistics classes. Now, notice here we have number 2 NPR, number 3 is NCR. And again, C stands for combination. If you go above, just to kind of look at that, NPR, the P in NPR stands for permutations. So what we're doing is combinations. Okay, so here I'm going to hit enter. And that's going to be 8C. Now I'm going to type in 5, right? And that's N8R5. So that's 8 choose 5 and hit enter. And there you go, 56. Let's do number 26. That was 35 choose 2. So again, you hit the number first, then you call on the combination function. NCR, enter. And this time I'm going to type in a 2 and enter. There you go, 595. That's what we had. Now, something interesting here, folks. If you subtract 2 from 35, you get 33, right? Check this out. If I go 35 math, and instead of 35 2, I'm going to type in 35 32. I'm sorry, 33. That's 35 minus 2 makes 33. And look what happens. Exactly same number, huh? So combination 35 choose 2 is the same as 35 choose 33. As long as you subtract those two numbers, that's what this is. So do again 35 minus 2, that would be 33. Look at the top one, combination 8 5. I'm going to do combination 8. 8 minus 5 is 3. I'm going to do 8 3. The answer is going to be 56. So I'm going to do 8 math, go to prop, NCR, and instead of 5, I'm going to type in 3. See that? Boom, 56. So this is something that actually we're going to look at when we do the binomial theorem. We're going to recall these things. Okay, so please keep that in mind as we go through this work. So now we're done with this part. We haven't talked about the binomial theorem, but we will in just a moment. We're going to talk about the binomial theorem. Okay, so let's talk about now the binomial theorem. Now, before again we talk about the binomial theorem, let me move that away from our work, because again this is the exercise we're going to look at the very end. Okay, and let's work our way towards the binomial theorem. Now, here is the objective of what we want to do. Okay, so let me actually write down what we're trying to do here. The objective is to actually expand a plus b, here's the word binomial in the binomial theorem, a plus b to the n. That's all we want to do. Pretty simple task, huh? So for example, let's say we're going to begin by this. Suppose I want to do a plus b beginning with 0. Well, a plus b, a and b are numbers, by the way, here. Now, two numbers raised to 0 power are 1, right? Makes 1. So I'm just going to write 1. Now, actually, I spaced it out away from 1 for a reason. This is how we actually want to do this. Let me, in fact, move it over even more than that. Okay, I'm going to put it right here. Usually we do that, right? We write in front of equal sign, but I'm doing it for a reason. Now, let's take a look at this one. Next, we're going to look at a plus b to the first power. Now, this time, anything to a first power is going to be itself, right? So a plus b to the first power is going to be just a plus b, which again, ordinarily, isn't that how we would write it? But actually, I'm not going to write it like that. I'm going to move it away from this as 1a plus 1b. Okay, and let me go further and actually do this. Here's 1, 1, 1. I'm using color for those numbers. Let's do another one. Let's do a plus b squared. You kind of see where this is going, right? I'm increasing the exponent from 0 to 1 to 2 to 3 and so on. Now, a plus b squared, we actually remember, we have memorized how this goes. Remember, the square of a binomial is a squared plus 2ab plus b squared, right? And there you have it. Now, let's say I want to do a plus b cubed. A plus b to the third power. Now, for this one, because we didn't have a formula for it. So one way I can do this, let me go to the side and actually do this. Okay. To do a plus b cubed, I'm going to have to do a plus b, a plus b, a plus b. And you kind of see now why we need this binomial theorem. As the exponent grows, it's going to be harder and harder to multiply these binomial expressions on the right side. Imagine if I want to do a plus b to the fifth power. Now I'm going to go a plus b dot 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 5 times, right? Now each time I have to, let's say, however I'm going to do this, it's going to take a long time trying to multiply these out. Now, but suppose I did on a piece of paper. I went ahead and multiplied these out. Okay, this is what it's going to look like for a plus b cubed. The first number is going to be 1, and the term is going to be a cubed plus the next number I got was 3. Again, I'm not showing you how I got that, but that's actually legitimate. What I got is 3a squared b. The next number I got was, after I multiplied, combined like terms, and did all that good stuff. Okay, this is what I got. And here's b cubed. Okay, now let me show you one more. Okay, a plus b to the 4th power. And to do that, so it fits in on a line, let me remove this expression. So next, I did a plus b to the 4th power. For a plus b to the 4th power, again, the first term is going to be 1a to the 4th. Again, I did this the hard way, okay, by multiplying a plus b by itself 4 times. And I got 4. Then it became a cubed b plus. The next number turned out to be 6. And it became, it became a squared, b squared plus. Then it became 4 ab cubed plus, the last number was 1b to the 4th. Okay, now you kind of see how this is going to go. There's actually, now at this point, let's look at the patterns that we see in order to do a plus b to the 5th power. Let's say we want to do that one next without doing it this way. I don't want to do a plus b, a plus b, a plus b like that. See, we do not want to do this. That's, if you do that, that's going to be a nightmare. We don't want to do that. Okay, so how are we going to do this? Now, drawing the patterns that we see from what lies directly above a plus b to the 5th power. Let's take a look at a plus b to the 4th power. And in fact, if you look at the whole thing here, if I look at this whole thing, what I have so far, it looks like all the numbers in front, the first term, are 1. The numbers in front of the last term is going to be 1 also. For a plus b squared, you have a squared, b squared. A plus b cubed, you have a cubed, b cubed in the last term. A plus b to the 4th, you get a to the 4th, b to the 4th. So I guess it makes sense that the number is going to be what? 1a to the 5th plus 1b to the 5th, the last term, right? I'm over here and then I move to the right. Now, if you look at the other patterns that you see here, this 2 actually, this turns out to be the sum of this one and 1 directly above it makes 2. Look at the next row, the next line, if you will. There's 3 here. 1 and 2 add up to 3. 2 and 1 adds to 3. In the next row, next line, 1 and 3 makes 4. 3 plus 3 makes 6. 3 and 1 makes 4. So let's continue on this pattern. So the next term in expansion of a plus b to the 5th is going to be what? 1 plus 4, right? That makes 5. And then I'm going to have ab plus. I'll put the exponents on a and b in a minute. I'm just going to work the numbers, the coefficients. 4 and 6 makes 10. I'm going to put ab. 6 and 4, right? I did 4, 6 got 10. Now 6 and 4, these two, makes up 10. So that's going to be 10. Again, put ab. And then 4 and 1 here, 4 and 1 makes 5. So I'm just going to put 5 and then ab again. So we got the coefficients. Now, let's take a look at the other pattern that we see here. If you look at the exponent on a, in a plus b to the 4th, it begins with 4, then it goes to 3, 2, 1, to nothing, right? So it's going to continue on that pattern in the next line. A to the 5th, next term, 4, 3, 2, 1, if you will, which we don't usually write. Now look at the exponent on b. Starts with 1, then it's 2, 3, 4. Or if you look at it the other way around, it's 4, 3, 2, 1 to nothing. So it's going to go 4 from the right to left. 4, 3, 2, 1. And there you go. We have the expansion of a plus b to the 5th power without actually doing this. Again, we do not want to do this. Imagine if I have a plus b, I don't know, to the 10th power, to the 9th power. We'll do one of those later. So that we don't want to multiply them by multiplying the binomials actually themselves. Now let's take a look at other patterns you see in this on a plus b to the 5th. If you count the number of terms in a plus b to the 5th, the exponent is 5, right? Look at the number of terms. 1, 2, 3, 4, 5, 6. So there's one more term than the exponent. Look at a plus b to the 4th power. This one. How many terms you see now? 1, 2, 3, 4, and 5, right? Again, one more than the exponent. So that's the other thing that we just noted. Let me remove these out. Oops, I didn't want to remove that, but that was easy to fix. That's b to the 4th. Okay, and finally, the last observation here is the following. If you look at the exponents, 5, 4 and 1, 5, 3 plus 2, 5, 2 plus 3, 5, 1 plus 4, 5, and of course the last one is 5. All of those exponents should equal to the exponent that you see in a plus b to the 5th power. It's going to add up to that exponent. Okay. So again, you can see a lot of interesting properties for what we just did. Now, unfortunately, what happens is this. Let's say I want to do a plus b to the 9th power. Well, if I do this approach, that means I gotta know a plus b to the 8th. To know a plus b to the 8th, I gotta know a plus b to the 7th, right? To know a plus b to the 7th, I gotta know a plus b to the 6th. So this is not really a practical way of doing things, is it? So we actually want to do it in a more efficient way. But we're going to draw inspiration from what we just saw. Now, the thing that we need to actually find out is this. The pattern that we see for terms remain the same. What we need to actually figure out how to do are these numbers, these coefficients, without having the numbers that are directly above them. You see that? Without knowing those. So, now in order to do this, let's actually do an example. And in my example, I'll show you where these numbers come from. And then we will actually talk about the binomial theorem. Okay? So, let's actually do expansion of a plus b to the 7th power. Okay. Now remember, I don't have a plus b to the 6th power, right? The row before it that I need. But again, we know a number of patterns. We have observed a number of patterns in the expansion. So let's actually write down what we know so far. We know the first term, right, folks? It's going to be a to the 7th, isn't it? Now, for the next term, do this. Draw a fraction line and then put a and b together, right? And why? Because if you look at, for example, in a plus b to the 5th, if you look at this one, sorry about that. If you look at a plus b to the 5th, you see ab are side by side, ab, ab, ab. Other than 2nd, 3rd, 4th, 5th, the first and the last terms are by themselves, just a to the power of n, which is 5, and b to the power of 5. In between terms, we'll have AB, 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 AB. So again, we're going to generalize that. And how many terms we're going to have? The exponent is 7, isn't it? That exponent is 7 right in here. So we're going to have 8 terms, correct? 8 terms, one more than the exponent. So that's 2, 3, 4 terms, 5, 6 terms, 7 terms, and remember the 8th, which is the last one, is going to be b to the 7th power. So total, I have actually created a template that has 8 terms in it. Correct? Just to make sure. Here's 1, 2, 3, 4, 5, 6, 7, and 8. Now, let's take a look at the exponents. Remember the patterns that we saw in a plus b to the 5th. Look at again a to the 5th. Then it goes 4, 3, 2, 1, right? So we're going to do that. The patterns we see. I'm going to use color on this for the reason. So I'm going to go 6, 5, 4, 3, 2, 1. And remember the pattern that we saw on B's. The B's go the other direction. It starts from right to left. You have B to the 7th, then it's B to the 6th, B to the 5th, 4th, 3rd, 2nd, 1, and then down to nothing. Okay. So we actually have all the terms. What's missing is the number in front of it. Okay. Now, these numbers turn out to be the fractions we're about to write. Every one of these fractions, their numerator is going to be 7, which is the same as the exponent on the binomial. And then factorial, 7 factorial, factorial, move that out of our way, 7 factorial, 7 factorial. You see how that works? We are working off of the pattern. Now in the denominator, and that's why I use color in the denominator. So A6B1, put 6 factorial. That one, red one, put 1 factorial. Okay. Then I have 5 factorial, 4 factorial, 3 factorial, 2 factorial, 1 factorial. The red numbers. This is 2, that's 2 factorial, 3 factorial, 4 factorial, 5, 6 factorial. You see how that goes? And now we have our fractions all written down. Okay. Now, the other pattern that you see here, this factorial isn't cooperating with me. There you go, that's factorial. Okay, now here's another thing that we observe going back to a plus b to the 5th, this one. If you look at this expression, 1, 2, 3, 4, 5, 6, right? Look at the middle, split in the middle. That's right here, split the center. If you look at the numbers that are on either side, look at that. You see the symmetry in these numbers? So that's really cool. There's so many things, so many patterns that emerge from this expansion of binomials. And there you go. Same thing happens in the row above it. 6 is in the center. Look at on either side you got 4, and then you have 1. So we're going to again tap into what we just saw. Okay, and let me remove the blue marks. And even, oops, these dots, I'm going to remove them. Sorry, I know I got rid of some of the things, but they're easy to put back on. Okay, so let's actually do that now. Now, and what the implication of that is the following. The symmetry we saw in the coefficients are actually going to be here also. That's going to be our binomial theorem. In a minute, we'll see that. So, now here's how the fractions work. With fractions, we're going to have, I need to do these fractions now. 7 factorial, 6 factorial, 1 factorial, right? If you want to do it on your TI or whatever calculator, this is combination, C7, and we're going to go 6. Okay, which is going to be exactly the same as, remember by symmetry, let me draw for you. I'm looking at this fraction. That fraction is exactly the same as that, isn't it? So if we find one of these, we find the other one. And remember again, C7, 6 is equal to C7, 7 minus 6 is 1. And this I can do. I don't need a calculator for this, right? That's 7, 6, 5, 4, 3, 2, 1. Divide by 6 factorial. 6 factorial is 1. And we're going to cross 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then it's just 7. And there you have it. So both of these numbers, these fractions I have circled in blue, are going to be simply 7. Let me remove the blue marks now. Okay, now let's move on to the next fraction. This fraction and this fraction are going to be exactly the same. True? Let's try those. That's going to be 7 factorial divided by 5 factorial 2 factorial, which means 7, 6, 5, 4, 3, 2, 1 divided by 5, 3, 2, 1 and then 2, 1. Right? And of course make sure you put those dots in there. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, cross out. And of course the 2 and the 6 cross, the 2's cross out. 3 times 7 makes 21. There. So we got 2 more fractions worked out. What we just did was actually, if you want to do it on your calculator, we did numerator is 7, right? So we just did C7, 5, which same as C7, 2. Remember, 7 minus 5 would be 2. So you can do either or. Let me erase the blue marks. Now, let's move on to the next fraction. That's 7 factorial 4, 3. And that's going to be exactly like the one that's next to it, right? These are the same. So let's do that one. And this one turns out to be 7 factorial 4 factorial 3 factorial, which means 7, 6, 5, 4, 3, 2, 1. 4 factorial 4, 3, 2, 1. 3 factorial 3, 2, 1. Again, 1, 2, 3, 4, 1, 2, 3, 4 crosses out. If you do this correctly, by the way, yes, this will happen every time. What will happen? What will happen is everything in the denominator goes away. All the factors of denominator, notice these 3 examples I just did, all of them go away. You only have numbers in the numerator. You got the 7 and the 5. Makes 35. So there you have it. We got these numbers down. Okay. So now we can actually finish off the coefficients, and we're done with the expansion. And of course, let me move these out of our way. We'll get to these later in just a few minutes. So let me do expansion of a plus b to the 7th now. This is the complete expansion, okay? With those coefficients put in, the numbers in front. A plus b to the 7th is a to the 7th. 7a6b. Next number was 21. A fifth b squared plus 35. A fourth b cubed plus 35 a cubed b fourth plus 21a squared b fifth plus 7ab 6, and finally plus b to the 7. There you go. Of course, as the exponent grows, so does the number of terms, right? Now, one thing, by the way, just so you see from here, one quick conclusion. A plus b to the 7 does not equal a7 b7, does it? Right? This is not right. Look at it. Has, of course, it has a7 here, b7, but look at how many terms we're missing. We're missing all of these terms right in here. So just be really careful with that. That does not work. And don't worry, I'll tidy this up. There, looks better, huh? So now, if this was, since we're talking about this, if this was a times b, the product multiplication, then that would be a7 b7. But that property does not work. It does not hold with addition. right? It doesn't work. There you have it. Okay, now, so we're done with the expansion of a plus b to the 7th. Now we are in a position to actually talk about the binomial theorem. Okay, now, let me write the binomial theorem, and then we actually look at how the book does it. Let me move that away again. So this is what now the binomial theorem is. Let me write it. The binomial theorem. This theorem, by the way, if you take again statistics, you will see this, some form of this theorem in your statistics course. In that course that some of you are going to be blessed to take, one of the probability distribution is the binomial probability distribution. So you will see not this theorem, but you will see a form to find expression of one of these terms. So you'll see this nonetheless, you'll see it again. Just want to make sure of that. Okay, so here's what the binomial theorem says. In the expansion of a plus b to the n. Okay, now check this out. This is so cool. The coefficients are n0, and then we have a to the n plus the next coefficient is n choose 1, a to the n minus 1b. The next one is n choose 2, a to the n minus 2b squared, and so on and so forth. Now, I don't expect you to memorize this theorem, right? We don't want to memorize it actually, but we want to be able to use it. So remember, we went off of a pattern that we saw. So that's what we want to do. But I'm going to write the theorem just so you have it. So this continues on. The term before the last term is n minus 1. And a b to the n minus 1 plus the last term is n b to the n. Pretty fancy, huh? And there you go. That's the binomial theorem. Now, all of this lengthy expression, amazing. We can actually write this in a more concise form using sigma notation. This is not in your book, but again, it's good to know. You're going to go off the pattern like we did a plus b to the 7th, okay? That's your easiest way to do it. But I'm just going to give this to be complete for your notes. So this is going to be given by n choose k, a to the n minus k times b to the k power. Okay, and there you have it. And in here, of course, k goes 0, 1, 2, ... all the way up to n. That's what k does. Okay, and here is the binomial theorem. Okay. Now, we can actually write the expansion of a plus b to the 7th, right, using this. The expansion of a plus b7. Oh, let me show you. Now I'm actually at this point where I can actually show you the binomial theorem. This is what's in your book. Now, hopefully this makes sense and you can relate to this. This is the binomial theorem. There are two forms in your book. Don't worry about the first form. It's in there. It's on page 919, I think. Let me see. It's on the bottom of page 917. If you have a book, if you want to look at it, but this form is better to use. Notice the authors do not use summation notation, but since we talked about sigma notation, why not? Might as well use them. And it just makes it look nicer and more concise. Okay, so let's see, what do I want to do next? So this is again the form of the binomial theorem, and I was going to write actually a plus b to the 7th in this form. So a plus b to the 7th becomes 7, 0, a to the n is 7, plus, isn't this cool? 7 choose 1. Those are the coefficients now. A 6b. Next coefficient, 7, 2. A fifth b squared. Next, 7, 3, a fourth. See, I'm talking, thinking, doing a whole bunch of stuff here, and writing. And what I mean by that is that I'm not really thinking, I'm just drawing on the pattern. So it's so easy. If you recognize the pattern, you can do this. And a squared, b fifth. Next one's going to be 7, choose 6, a, b 6, 7, choose 7, b 7. Now, the other thing that you see here, by the way, in this expression. Okay, if you look at, let's say, the number here and the number here are the same, huh? 2, 2, 3, 3, 6, 6, 7, 7. You see that? So the number on the bottom of that in R notation matches the exponent on B. Again, all of these little tidbits help me just kind of remember what I'm doing. So let me remove those little blue circles now. Okay, and if I by mistake remove something else, don't worry, I'll plug them back in. Okay, which I have. So that's 7, 2. This was 7, 3. That's the parentheses missing there. Anything else I took out? No, 7, 0, 1, 2, 3, 4, 5, 6, 7. A7, A6, A5, A4, A3, A2, A1. And B7, B6, 5, 4, 3, 2, 1. And perfect. There you go. This is your full expansion of A plus B to the 7th. Okay. Now, that's what that is. Now, the other thing, let's see what else we want to look at. Let's actually look at an exercise. How's that? Okay. Now, in our exercise, let's take a look at exercise number 28. Again, if you're getting tired of the video, feel free to pause it. Go do something, come back and watch the rest of the video. That way you're not getting too tired. Okay, let's actually look at this next example. In this example, we're going to look at exercise number 28 in your textbook. In exercise number 28, the question is asking you to expand the binomial. Okay, the question reads, expand. Now, in the exercise, they say use both of the methods shown in the section. We're just going to use this method I just showed you. Okay, the expression actually pretty manageable. M plus n to the 5th power. Okay, you're doing exercise number 29, so this is very much like yours. Okay, so for this one, remember how this is going to go. It's going to be m to the 5th, right? First term to the 5th. There's going to be 6 terms in the expansion. Remember the coefficients. Go 5, 1, m4, n. Next, 5, 2, m cubed, n squared. Next, 5, 3. See, each time the exponent on m drops by 1, n picks it up, right? Plus 5, 4, right? We went from 5, 3 to 5, 4. That's going to be m n 4th. And then plus, last one, if you want to write it, there you go, 5, 5, n 5th. And even in front, I didn't write it, but in front is 5, 0. Now, you can actually verify this. You can do it on your calculator. 5, 0 equal 5, 5. Both of these end up being 1. That's why we have only 1 in front of the first term and 1 in front of the last term. Now, if I do actually these 5, 1, 5, 2, 5, 3, 5, 4, 5, 5. Well, 5, 1 is going to be, you can use your calculator. That's C5, 1. It's going to be the same as C5, 4, right? 5 minus 1, C5, 4. And when you do this, you're actually doing right up here 5, 1 and 5, 4. Those numbers are the same. When you do 5, 2, and that's going to be the same as 5, 3. Okay, so you can actually do it on your calculators again. If you do 5,2 equals C5,2 equals C5,3. Those are going to be the same. Okay, and I'll actually do them without a calculator. Now 5,1, this one, that means 5 factorial, 1 factorial, and 5 minus 1 is 4 factorial. That's going to be 5, 4, 3, 2, 1. 1 factorial is 1, 4 factorial, 4, 3, 2, 1. Right? 1, 2, 3, 4, 1, 2, 3, 4 crosses out, so this is just going to be 5. C5,2, that's going to be again 5 factorial, 2 factorial, 3 factorial. Okay. 5, 4, 3, 2, 1. 2 factorial, 2 times 1, 3 factorial, 3, 2, 1. The 1, 2, 3's cancel. Also, 2 and the 4, the 2's divide out, so this is going to turn out to be 2 times 5, 10. Good. So there you go. Now I'm just going to put those quantities in the expression. Remember, 5, 1, 5, 4, I use red on that. That's this one. The green dots were 5, 2, 5, 3. Those are these numbers that we got. That's in green, and this is in red. Okay. So now I can actually complete this. Let me move that out of our way out there, so we don't have to see it again for a while. And now I can actually write the expansion, folks. So the expansion of m plus n to the 5th will be m to the 5th, and then remember the there comes 5, 1. 5, 1 is next, right? I'm looking at this expression here. 5 choose 1 is next. So that's going to be 5. Exponent decreases on m, and n begins with 1. The next number would be 10. M decreases by 1, n increases by 1. Plus 10. M squared n cubed plus 5 m n 4th plus n to the 5th. And there you go. So I can again check that I did this right real quick. I had 1, 2, 3, 4, 5, 6 terms, one more than 5. The exponents, each of these add up to 5. See, 5, 4, and 1. Right, this exponent is 1 if it's not written. So there's 5, 5, 5. And this is also 1 and 4 makes 5. So those exponents add up correctly. I see the symmetry in the numbers. That looks good. Right, and even 1 and 1, so there is perfect symmetry there, so it looks like we actually did these correctly. Correct. And there's the expansion. Now let's take a look at, so we're done with this one, everyone. That wasn't so bad. Again, for some of you, if you want to go slower, what you want to do is you want to look at one line, pause the video, digest it, look at the line, write it down, again contemplate on it for a few minutes, and then restart the video, look at the next line, and this way you're going at your own pace, not my pace, because I cannot slow down too much. It's just going to make the video unwarrantedly too long. Okay, in number 36 we want to do the expansion of x plus 2 over y. You do number 35, I believe. To the 9th power. Okay. Now for this one, again, for 2 to the 9th power. Remember, the first term is going to be x to the 9. The last one is going to be 2 over y to the 9th. And here are the patterns. It's going to go 9, 1, x 8. And then 2 over y kicks in. And instead of a and b, we have x and 2 over y. It's not always a and b, it can be something different, as long as it's a binomial expression. Plus 9, 2. X is going to lose 1 exponent. 2 over y is going to gain 1. Next, 9, 2. It's going to go 9, 3, x6, 2 over y cubed. Next, it's going to go 9, 4, x fifth. See, I'm just looking at the pattern that's going on here. Then it's going to go 9, 5, x4, 2 over y to the fifth plus. Next, it's going to go plus 9, 5 becomes 9, 6, x cubed, 2 over y to the sixth plus 7, x 2 over y to the seventh plus 8, x 2 over y, 2 divided by y to the 8, and then remember the last term is the second term in the binomial to that power. And there you go. We should have 10 terms in this expansion. 10 terms. Now, I use my calculator. You can use your calculator to do all those coefficients in front. Okay? And so that's what I did next. Let me show you what I mean. What I did. Next, I did these. I did 9, 1. Now 9, 1 and 9, 8 will be the same, right? 9 minus 1 is 8. Both of these turn out to be 9. On my calculator, I did 9, 2. 9, 2 is 9. Well, 9 minus 9, 7. Those coefficients will be same. 9, 3. Again, 9 minus 3 is 6, right? 9, 3, 9, 6 coefficients will be the same. That number turned out to be 84. I use my TI calculator, folks, for this. The NCR 9.4 and 9.5 would be the same for this. I got 2,520. Okay, just to make sure, that's 9.5. Oops, actually, sorry, I didn't do that right. 9 and 5, that's 126. Sorry. But the rest of them are correct. Okay, that turns out to be 126. Let me just to make sure. 9.3, 9 NCR3 on my calculator. I got 84. 9.2, 36, and 9.8 is 9. Okay, and there you go. We got all of these coefficients that go in the lines directly above this. So the expansion is going to look like the following. It's going to be x to the 9th plus, then 9, 1 kicks in, right? 9, x 8, and this is 2 over y, plus 9, 2 kicks in, 36, x to the 7th. You lose one exponent on x, you gain an exponent on the fraction. Then 9, 3 comes in, 84. Lose an exponent on x, gain an exponent on the fraction. Next, 9, 4 kicks in, 126. X fifth, 2 over y, fourth, plus. So we just did 9, 4. Then 9, 5 kicks in, 9, 5, 126. Lose an exponent on x, gain it on the fraction. Long, tedious process, right? It's not, I don't think it's difficult. It's just long and tedious is what it is because the exponent is so high. Now, don't worry, by the way, on your exam, you're not going to do something that's this long. Okay, next, I just did 84. That was 9.6. Now I'm doing 9.7. 927. And this is what I mean. 927 is here. That's 36 x squared, 2 over y to the 7. See, that's how I know it's 9.7. That second term matches the lower number on the NCR. 9.7. Next, we're going to do 9.8. 9.8 is 9. Lose exponent on x. 2y to the 8. And let me finish it on this line. Plus, the last number is going to be 2 over y to 9 power. Okay. Now, next, x to the 9 plus. Now, this next term, let me actually show you. This, I'm looking at that term. Okay, so for this term, I'm going to do 9 times 2. That makes it 18, right? So I'm going to get 18 x to the 8, correct? Plus next term. That next term is going to be this one. When you square the 2, see in here, 2 gets squared. That's 4. Then it multiplies by 36, right? So 36 times 4, that's 144. This is going to become 144 x 7. And then y becomes squared, right? Y squared. Now look at the pattern that's emerging on the variable size. I have x9, x8, x7. So it's going to go x6, 5, 4, 3, 2, 1. Y is picking up the exponents, right? It's going to be y1, y squared, y cubed, y fourth, and so on. So the only thing is really the coefficients I got to deal with in here. Okay, so we're done with this one now. Next, I'm going to looking at this term. 2 cubed is 8, right? I'm looking at, again, in here. That's 2 cubed 8 multiplied by 84. That's 672 times, it's going to be x6, y cubed, right? Let's see. The next fraction, let me get rid of this one now. Now I'm looking at this one. So again, I have 2 to the 4th power. That's what 2 to the 4th is, 16. Multiplies by 126, makes it 2016, rather large number. Oops. 2016 times, and this is going to be x to the 5th, y to the 4th, plus. Done with this one. Okay, the next term is down here. Plus 2 to the 5th, that's 32. 32 times 126, that's 4032. Plus 4032, the fraction is going to be x4, the denominator gains. Notice the numerator is losing one exponent every term. We go forward and the denominator gains 1. So we're done with this term, right? With this one. Now we're looking at this term. Okay. In this term, we have 2 to the 6th power. 2 to the 6th power is 64 times 84. That's 5376. 5376. X is going to be cubed. Y is going to be 6 plus. The next one is going to be this one. 2 to the 7th. Well, 2 to the 7th is 128 times 36. That's 4,608 times, it's going to be x squared and then y 7th. And almost done, folks. Hold on. And all good things come to an end, including the binomial theorem. Okay, let me do 2 to the 8. 2 to the 8 is 256 multiplied by 9. That's 2,304. 2,304. And it's going to be x over y to the 8. And finally, 2 to the 9th power. That's going to be 512. And it's going to be divided by, you can write it as 1 over y to the 9th, or let me write it as this. Let me just write it as a fraction, okay? So it's going to be 512 divided by y to the 9th, because there is no x, right? It's going to be at this point, it is, if you want to write it as x to the 0, but that's just 1. So for that reason, we don't need it. Boy, and there you go. Check it out. Now, on the homework, again, you're doing 35. It's kind of like this one, but on the exam, we probably keep it to the 4th power, no more than 4, maximum 5, like number 28, like this one. This wasn't so bad, right? Nothing looks bad compared to number 36 now. Okay, we're almost done, folks. We're almost done. I know it's been a long video because there's so much in this section. Now, to finish this off, let me actually, this is the last example we're going to do. I'm still away from that. Now, what we want to do is this. Sometimes we don't want the full expansion like we did here. This expression, number 36, we don't want to do to the 9th power all the way to the 9th power. We want just a single term in the expansion. Just a single term. Okay. Now, let's take a look at this a plus b to the 7th power that we did. This is a good one to actually look at. So I'm just going to copy this one if I can. Oh, it's not cooperating with me. Okay. Let me see. I'm not sure what happened to that expression. It's just vanished, huh? Okay, let me take back. And there you go. It's back. Worked like magic. Okay, I see. So I'm going to actually do this. I'm going to copy this expression if I can. Hopefully it will copy correctly. If not, I can attach it. I'm going to copy it down here. Okay. And there you go. Now for this one, I know this is going to be a b 5th, right? Just to make sure. a7, a6, a5, a4, a3, a squared, a1. Okay, b1, 2, b1, 2, 3, 4, 5, 6, 7. Perfect. So it's down here. Now, check this out. Let's say we don't want a full expansion. Suppose I just want to know in this expansion, let's take a look at the 5th term, a single term. 5th term. That's what the one I want to look at, the 5th term. Now, 5th term, that means this is going to be 1, 2, 3, 4. This is the 5th term, isn't it? Okay, so let's take a look at actually that term. I'm going to write that term down. 35 a cubed b 4th. Okay. Now, if the question asks find the 5th term, let's take a look at the pattern we see in the 5th term relative to a and b. Don't worry about this 35 for now. Now, for the 5th term, right? This is 5. Oops, sorry. This is 5 for the 5th term, right? That's 5. So if you look at 5 and look at the exponent on b, 4, 1 less than that. You can see this pattern in other terms. So look at the 4th term. For the 4th term, b is 3. Okay, so this works for all terms. But looking at just the 5th term. So the exponent on b is 1 less than the term number. So in other words, if I was to start this from scratch, I'm going to put a, b side by side. Right? Every term in between first and last term will have a and b side by side. Because we're looking at the 5th term, so this is going to be 4. And remember, some of the exponents in every one of these, every one of them, some of the exponents has to be 7, right? This is going to be 7, 7, 7, 7. So, this is 4, so that means the exponent on a must be 3 to add up to 7, right? Which is exactly what this is. Now that 35 in front, how did we get that 35? Well, the 35 in front, that's when we had a fraction We moved 3 factorial, 4 factorial, the numerator was 7 factorial, and there you go. That's how we got that 35. Okay, and now we can actually write any term in an expansion based on the pattern we just saw. So let me make up an example here, okay? An example. And then we'll look at the exercise in the book. In this example, let's say I'm doing m plus n to the 12th power. Don't worry, we're not going to expand this. The question is find the 9th term in that expansion, a single term. So for the 9th term, again, m and n will be side by side. Here's the fraction in front. The exponent on n is going to be what? This is 9th term. The exponent on n is going to be 1 less than that. It's going to be 8. Right? The exponent on m, what is that going to be? Remember, some of these two exponents have to be 12, right? So the exponent on m has to be 12 minus 8, or 4, doesn't it? Okay. And now I can put that exponent 4 here. See, 4 and 8 makes 12. Next, I'm going to copy and paste 4 and then 8 factorial down here. The numerator is going to be 12 factorial, which is going to be exactly the same as this. These will be the same. And there you go. So we have now the single term, the 9th term, without going through the full expansion. Next, I can do my factorials, right? 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 4, 3, 2, 1. Here's 8 factorial. We're going to cross those out. 4 times 3, 12. The 3 cross 12 cross out. And then we have the 2 and the 10, you get 5. And the product is 5 times 11, 55, right? 55 times 9 is 495. That's what that number is. So the answer to the 9th term here is going to be 495, M4 in 8. That's a single term in the expansion. Okay, and that is the one that I made up. Now let's take a look at a couple in the book and we'll be almost done. I'll save the best for last, number 63, which is not part of your exercise. Okay, so 2 more and we're done with this section. Okay, let's take a look at number 46. In number 46, the expression is, we're given x minus 2 to the 12th power. The question reads, find the 11th term in the expansion. So 11th term, you're going to have x and negative 2. See, these are the 2 terms in here and in here. So those are going to be side by side. Now remember, for the 11th term, what is this exponent going to be? That's going to be 1 less than, isn't it? So this is going to be 10. The exponent on x is when you do 12 minus 10. You look at the difference between these two numbers, right? The difference between these two. That exponent is going to be 2. Good. And we have that one. And then we can actually write our fraction. That's going to be 2 factorial, and then we're going to go 10 factorial. You see how that second term unlocks everything. And the numerator, of course, is 12 factorial. 12, 11, factorial on top, 2, 10 factorial on the bottom. Whatever they are, huge numbers, but they're the same. They cross out, they cancel. 2 and 12, we get 6. 6 times 11 is 66. So this is going to be 66 x squared. Now, negative 2 to the 10th power. This I need to do it on the calculator. Okay. Well, negative to even power is going to be positive. So I'm just going to do 2 to the 10th. That's 1024, right? Times 1024. So the answer to the exercise is 1024 times 66. Makes it 67,584 x squared. And there you go. That's going to be the 11th term. Cool, huh? Now let's take a look at last one. This will be exercise number 48. In number 48, we have 1 over b squared plus c to the 7th power. The question asks you to find the value of the 4th term, see, a single term. So for this one, again, we're going to put the first term in the binomial side by side next to the second term in the binomial. For the 4th term, what's going to be the exponent on c? 4th term. It's going to be 1 less, right? So I'm going to go 3. That's 1 less than 4. This exponent on the fraction, remember these two, you subtract 3 from 7, we're going to get 4, aren't we? And that's what this is going to be. 3 and 4 make 7. And we are in a position now to create a fraction. Here's the denominator of the fraction. 4 factorial, 3 factorial. The numerator would be 7 factorial. And there you go. Now, again, 7 factorial, 765, 4 factorial. And then there is a 4 factorial on the bottom. Times 3, 2, 1. 3 and 2. So the 4 factorials are crossed out. 3 by 2, 6. The 6 crosses out. 7 times 5 is 35. So this is going to be, move this again out of your line of sight. There you go. So this is going to be 35. 1 over b squared to the 4th power. We're looking at this now. B squared to the 4th. That's b to the 8th. And then c cubed. Now putting it all together, we get the final answer is going to be 35 c cubed divided by b to the 8. And that is the answer to exercise number 48. And with that, we are done with these exercises. Again, if you want to do this on your calculator, this fraction, this would be your 7/4. You can do 7/4. You can do 7/3 and c n r, which is c n r. You can do any one of these on your calculators, and you will get this magic number 35. Okay. Now, hopefully you're good. Again, make sure you can pause this video one line at a time, scroll it up and down, however, and pace yourself according to your pace. Now, the last thing I want to do is actually that n choose r. Let's clarify, what are we exactly choosing? So this is what the n choose r means. Okay. This is an exercise in the book, which I didn't assign. I just want to give you a heads up on your statistics and why it's called n choose r exactly. What exactly are we choosing here? So, now this notation is used, and it's called n choose r. They tell you the reasoning here is because it can be used to calculate a number of ways in which set of r elements are chosen from a set of n elements. That's what that choosing is. You see that? Chosen. So, in other words, to paraphrase, what we're doing is actually we're finding, that's what NR is. We're looking at the number of subsets of size R from n subjects or elements. Okay, that's what the choose is. So this notation actually counts how many subsets are there. So in this exercise, it says show that there are exactly 5 choose 3 ways of choosing a subset of size 3 from the first 5 letters of the alphabet. Okay, so now let me remove some of this clutter so you can now read this. Now it says show that there are exactly 5 choose 3 ways, right? Well, what is 5 choose 3? First of all, let's see how many there are. That's going to be 5 factorial, or you can use your calculator, right? And 5 minus 3 is 2 factorial, so that's going to be 5, 4, 3, 2, 1. I went ahead and wrote this all out. 3, 2, 1. 2 factorial is 2, 1. And 1, 2, 3, 1, 2, 3, cross out. 2 and the 4, you get 2. 2 times 5 is 10. There are actually 10 subsets. That's what we're talking about. 10 subsets of size 3 from 5. And that's what they're asking. It says show that that's how many. In other words, show that there are 10 subsets of size 3. Well, let's show this. The show is actually an exhaustive list. That's what we're going to do. Exhaustively, we're going to list them. So here's actual list that we can come up with. A, B, C. That's one subset of size 3 from the first 5 letters of the alphabet. Then it's going to be A, B, D, A, B, E. Right? Here's how I'm doing this. I'm looking at A, B, pairing them with C, D, and E. Okay, that's what I did. Next, I'm going to look at the next pairing. So I did A, B, C, A, B, D, A, B, E. Then I'm going to go A, C and do that with D, A, C with E. Right? Then I'm going to do the same thing with B. So I'm going to go B, C, D, and then B, C, E. And then we're going to go C, D, E. So how many do we have so far? We actually have 1, 2, 3, 4, 5, 6, 7, 8, right? 8. So there's going to be 2 more, right? So we got A, B, C, A, B, D, A, B, E. Next, I can actually do these. B, C, D, which I did here. That's done. Okay, what else are we missing here? B, C, E, C, D, E, A, C, D, A. Okay, how about A, D, E, right? A, D, E. That's what I'm doing next. Then once we're done with that one, the last one is going to be B, D, E. And there you have it. And we just showed that there are 5 choose 3. There are 10 subsets of size 3 selected from those 5 letters of alphabet. And this is the kind of work you'll be doing in statistics classes that you will be taking. Okay, so hopefully you enjoyed that. I know I did. And as always, if you need to review, please do so. Scroll back to the beginning of the video. I know it's a long video, but then we really took our time and we thoroughly covered everything, right? Hopefully you follow all that we did. Again, if not, please rewind the video and again watch everything from the beginning. And sorry about this. And with that, we are actually done with this section, seems like. And we are done with chapter 14, by the way. Okay, so I'm just going to stop the video. And that concludes section 14.4 for us.